Hello, everyone. I'm Kate, and today we will be talking about data preprocessing, which is one of the very useful techniques to make sure that your model perform really well. So, how we will structure our talk today is first of all, we will introduce the concept of data preprocessing, why it's important, and what kind of techniques exist. And then we will discuss specific cases of audio data preprocessing and then image data preprocessing. Those concepts are very useful for all of your homeworks. So audio data will appear in homework 1, 3, and 4, and image data will be in homework 2. And then we will conclude with just a few questions to self-test your understanding of the concepts. Make sure you are ready for all your assignments. All right, let's begin. Let's first of all talk about what is the concept of preprocessing. Essentially, this is just when we take some raw data, apply certain techniques, and then get some transformed data, and then we feed this transformed data into the model. And the notion is like if we applied good and if we pick like good transformation preprocessing techniques, our model will perform better. That's why it's very important to invest very heavily into understanding your data and making sure it's well aligned with all of your goals you're trying to accomplish during your modeling process. All right, so let's briefly discuss about what kind of data preprocessing techniques exist. We can briefly categorize them into 4 different groups. It could be data cleaning, feature engineering, data transformation, and data augmentation. Let's talk about each of them separately. So the first one is data cleaning. This is basically when you get some kind of data set, just some original data set, and you fix some missing values, outliers, or noise, and you create a clean data set, which is free of all of this thing. Next one is feature engineering. This is basically when you come up with new set of features or new set of very valuable features that could have more has more importance for your model. You can do it in multiple ways. You can combine existing features into new one. You can convert some categorical data into some numerical format. You can apply even more sophisticated techniques, all for the same goal to make sure that your features are more meaningful. Then you can move on and do some data transformation. This is more about when you normalize your data, standardize it, or use some different scaling techniques, which sometimes also could be very useful. And finally, there is a concept of data augmentation. This is when you increase the dataset size by creating multiple copies of your original data, but also performing some transformation on top of that. The easiest thing to imagine is imagine you have just one picture and you create multiple copies of this picture, of the image, but you apply certain transformation. So like you just do some rotation, you flip some picture, maybe you change the color scheme or something. So originally, instead of having just one picture, now you have multiple pictures. And the common notion is like the more data, the better. So sometimes it may work really well because you can accommodate for different ways of images. And there are different ways how you can do this, depending on the type of the data. So the techniques for audio would be a little different from the images. And in this recitation, we will discuss all of them. All right, let's start with the audio data preprocessing. Before diving into the code, we can just discuss conceptually what we can do with audio data, and then we will look into the actual code. So the first, imagine you get some raw audio. It could be you can find it on the internet, maybe you recorded your own voice. And then when you visualize this waveform, it's called a waveform, and you will see that it will look like this. And the typical notion is that this is not the most meaningful representation of the audio data. And there's a common practice of transforming this audio into more meaningful format, which is called a MEL spectrogram. So what we do in this step, we take the original raw audio and we transform it into this format. It calls MEL spectrogram. MEL is from the melody or audio. Spectre is like frequencies, and gram is something like visualization. So this is like a visualization of frequencies of audio or something. And if you look at this in the picture, you will see that the time steps are exactly the same. Exactly the same between two pictures. Only y-axis changed. This is because we changed the representation of this audio data. So now it looks like you can see the particular time step, you will see the frequency distribution, and this is done typically using the Fourier transforms. Once we have this MEL spectrogram, we can create multiple copies of it and play and use different data augmentation techniques. For images, remember we use like different rotations or something, but for data augmentation, the common techniques are time and frequency masking. How we do this is, imagine we take we create a copy of the original data, and then we just mask certain time steps. We can imagine that in real time when we record the voice, and then maybe we got the connection was really bad or something. So it's kind of, we try to mimic the cases when we see that, oh, the audio wasn't really clear. And so we want to make sure that our model is not very confused when in real time it will see some kind of data which is not very clean. It will work for that as well. So what we can do with our data, we can kind of mask certain time steps. We can do exactly the same, but horizontally, we can mask certain frequencies, or we can do both. We can mask certain both like time steps and frequencies. And then we will create multiple representation of the same audio, just with different ways. So once we finish this step is kind of optional. So data augmentation, like, it's very encouraged to do this, because with right data augmentations, the model can perform really, really well. But like, it's really optional. After we do this, we can do one more step of feature extraction. We can extract MFCCs, which is even more collapsed and more rich representation of audio. It will look, if we visualize it, it will look like this. And then we can do another set of different transformation. For example, we can normalize the data, and then we will receive these transformations, this visualization. So all of this, we can just go through all of these steps. And then to make sure that like there's a common understanding is that like the step number 5, this type of data, it's more meaningful for our model, and we can get better results. All right, now let's look at the code, how we can actually perform all of the steps. The first thing we do, we just load the data. We just load any random audio from the internet. We save it on our Google Drive. And then if we want, we can use packages and play it. Like, we can play the audio and see.
What sort of evidence is logically possible?
Very short audio, just plays really briefly, just a few like words. What we can do, we can extract the waveform and the sample rate from this audio, just like some brief information about this audio. And then we can plot it. As we saw, this is just a waveform. Once we get this, we can move on and extract more meaningful information using feature engineering and feature extraction techniques. So we try to extract MEL spectrogram. There are multiple libraries available. They can do it for you. So you can pass the original audio, the raw format, and then you can obtain MEL spectrogram. If we plot this is exactly what we saw before. So now it looks a little different compared to the raw audio. Next, we move on and we can do some data augmentation. As we discussed, there are two types that could be useful, is time masking or frequency masking. Let's look at the time masking. Time masking is when we take the original data and we create a mask which is randomly applied at particular time steps. So we say like, oh, we create a copy of the original audio and say, oh, please, kind of at a particular time step, please mask particular time step. And this is all done randomly. So we can do it with a little function. And if we display it, we can see that, yes, it kind of worked and certain time steps are masked. And we can do exactly the same approach, but mask certain frequencies. As we can see here, and in this example, certain frequencies would be masked. We can do exactly the same, just combine them both. And in this example, both frequencies and time steps would be masked, some certain of them, not all of them. Next, once we did this transformation to the MEL spectrogram, we can move on and obtain MFCCs, which is also, we don't have to do it like manually. We can also use a library in the package. They can do it for us. So we just pass some data and we transform our data into MFCCs format, which, as we said before, it's just like more compact and more rich way to represent the audio data. And it's very common, and you will see them. We will be using this format of audio data into the homeworks. And finally, we can also do some normalization. So we can apply, just take one particular element and just extract the mean, divide by standard deviation, and you will see that your data will look a little different. And essentially, the interesting idea is that like you can experiment with all of these methods. You will see that sometimes using normalization will work better than the others. Sometimes using certain time frequency or other different augmentation techniques will work, and other times it doesn't work. So it's very important to experiment. But this is briefly the overview of everything you can do with audio data. Yeah, so it's very important to experiment, but yes, so thanks so much for listening to the audio data preprocessing topic. And next we will move on to the images. Thank you so much.